Hello, everybody. I would like to welcome all of you in this video session. Today, we will be talking about mat foundation. Okay, so at the beginning, I'll talk about the theory behind the mat foundation and how we can calculate all the design parameters from the for the mat foundation, and then I'll show you a couple of problems, and then I'll do a mat foundation problem in the board, and that might take a while because these problems are relatively bigger. I'm planning to give one of that math foundation problem for your project, so try to learn that one quite well. Okay, now let me share my screen with you, and then I'll just discuss the math foundation, different aspects of math foundation with you from that PowerPoint presentation. Okay, let me share the screen with you. I hope all of you can see my screen here. So this is a mat foundation here. In many cases, rather than spread footing, individual strip footing or individual spread footing, we use just one slab under the entire foundation. This is called like raft or mat foundation. There are some definitely advantage for that. We'll definitely discuss with that in the later part of this lecture. Okay, so first of all, you can see at many cases, many circumstances, it is desired to make a footing that can support more than one line. Okay, each of the line can have more than two, like columns. There could be 2 or 3 or 10 or 15, doesn't matter. But if the foundation supports more than two lines, 2 or more lines, then basically we call that one mat foundation. Okay. In many cases, the mat could be for the entire, like slab, entire foundation, or it could be like some part of the foundation. So this is the picture of a mat foundation. You can see this is the slab at the bottom, and then these are the columns here. So there are more than one lines here. So this is a mat or raft foundation. So use of mat foundation, when we use mat foundation. So first of all, if the spread footings have covered more than 50% of the building area, okay, the mat foundation might be more economical. Okay, just cutting separate or individual footing for each of the columns, or just cutting the whole area and then construct the mat foundation, that would be definitely more advantageous. Second thing, sometimes preferred for soil which has very low bearing capacity, okay, but the column support is very high. So in that situation, we use mat foundation because mat foundation could be compensated by the amount of soil we dig out from there. We'll talk about compensated, like foundation later on this lecture. But for now, just try to remember that one, that if the soil has low bearing capacity, but the load coming from the building is, high, then in that situation, definitely we can consider mat or raft foundation. Okay. So a mat or raft foundation is a combined footing that may cover the entire area under the structure or supporting several columns and walls in more than one line. Okay, but the entire, foundation is mat is kind of more common. Okay. So type of mat foundation. There are several types of mat foundation. So First of all, flat plate uniform thickness. So you can see this is our mat foundation here. This is uniform thickness. On top of that, I just put that column, and this is a two-story building, for example, okay? Now the second one, the flat plate thicken under columns, okay? So you can see this is your plate, but there are some thickened part here just below the columns, okay? Actually, this one should move a little bit away this side. So you can see these are the, sometimes we call that one pedestal at the bottom, okay? Why this one is a little thickened here? We'll discuss about that, because we see that when you put like a column on top of a slab, then basically the punching shear through the slab is the governing factor to find out the depth of the foundation slab. Okay, so many cases we see when the load is too high, then basically that would cause a very thick slab. So rather than doing the slab very thick, we just try to consider that slab is a little thinner, and then we add the pedestal at the bottom. Okay. So number 3 is beams and slab. The beams run both ways, and the columns are located at the intersection of the beam. So this is your one beam, another beam, another beam, another beam. So there is like 4 beams this way and 4 beams this way. And the beams are arranged in such a way that your column will sit at the intersection of the 2 beams. Okay. So in that situation, you can see you can make your slab much thinner, because the punching shear part will be taken by the, like the thicker part here. Okay. Number 4, the flat plates with pedestals. In that situation, you can see, for the same reason, that you just added some pedestals here rather than using beams here. Okay. You just use pedestals. But the biggest problem here is like when you use that one as a parking lot, then basically a lot of the space will be taken by these pedestals. Okay, so that's why we try to avoid that one most of the cases. And then number 5, you can see here that actually the columns are at the top of this section here. Okay, this is basically a slab basement here, and at the top of that basement you just build your house. But again, this is not that common too. Now, mat foundation over piles. Many times if the soil is too soft, then basically we can use piles below the mat foundation. So here, mats may support it with piles, which will reduce the settlement. Okay, if we see that there is a chance of huge settlements, then basically we try to transfer the load to a steeper layer. Okay, that's the first reason. There's a second reason for that, which is actually if you try to put your mat under the water, then basically there might have some buoyancy pressure that will try to push the building up. So in that situation, we also try to use piles so that the piles can hold it down. Okay. Now, factor of safety for mat foundation. First of all, the factor of safety should be used to calculate the net allowable bearing capacity. We know that all the bearing capacity equations are in terms of ultimate load carrying capacity, but we have to use a factor of safety for the allowable load that the foundation can carry. So usually the factor of safety for mat foundation in clay and sand, in both cases, it should be at least 3. Okay. But for clay, sometimes we can use like at least like 1.75 to 2 in very extreme condition, like when we know that the layers are kind of uniform and we do a massive subsurface, like investigation to make sure that there is nothing unknown there. In that situation, you can just use 1.75 or 2. But I would rather recommend you to use at least 3 for most of the cases. But for sand, actually, there is no shortcut way. Most of the time, you have to use at least 3 for normal use, okay? Now, depth of the foundation. This is the biggest change you can see. This is like a individual footing, spread footing here, spread footing here. If you make your ground floor here, then basically your depth of foundation would be from here to here only. And your B would be here to here only, okay? But for mat foundation, when you are using the whole thing here, then basically this is your B. So your B is much bigger here. And at the same time, you can see your DF would be from here to here. So your DF is also much bigger here. So when your DF is bigger, means like your surcharge pressure or effective stress at the bottom of the slab, which is equal to gamma DF, would be much higher, right? So if you think about your bearing capacity equation, so your Q is bigger and the third term, your B is much bigger. So you can see the bearing capacity of the mat foundation is usually much higher than normal, spread footing. With the wrap foundation are larger than those of the isolated spread footing. We are talking about the width B. B is much bigger. Now you can see when we are talking about this whole thing here, like this one is working with the depth of B here, okay? Now you can see that for a spread footing B, let's say this is like 5 feet, then what will happen, only this influence line will just go with the influence of this foundation will go only 5 feet here, okay, if your B is 5 here. On the other hand, let's say this is 25 here. Then you can see actually this influence of that foundation will go 25 feet, okay, which is much higher than normal spread footing. So what is the advantage of that? We know, like if you go down to the soil, actually your bearing capacity increases. Why it increases? Because as you go down, your soil is more compacted by the soil above it. Okay, so in the surface, there is no load there, so it doesn't compact that well. If you go down and down, then soil will be compacted by its own weight. So that's why we see as you go down, your bearing capacity is increasing. Okay, so that's why a larger width of the wrap foundation or mat foundation will definitely cause a higher bearing capacity. So this one is the same thing. This one is talking about the stress increasing in the soil below the foundation depends on the width of the foundation, as I showed here. Okay, and then for a wrap foundation, the depth of zone of influence is likely to be much larger than the spread footing, as I showed it here. Okay, and the other important factor is like the loose pockets. If you have loose pockets here or like something here, there might be like, or like any of that here, then you can see there is a chance that this one will settle, not this one. And that could cause like differential settlement. But here, when you see the small portion doesn't have, but the thickness of that slab is huge, and the slab has enough stiffness, so a little variation in the bearing capacity along the horizontal extent doesn't affect that much because of the mat foundation. Now, bearing capacity, how we find out the bearing capacity of the mat foundation. You can see that this is the same equation that we use to find out the ultimate bearing capacity. But you can see here is our B, that would be much bigger for our mat foundation, and Q would be much bigger because Q is equal to gamma DF. If DF is bigger, then this one is bigger. But most common cases actually we use for spread footing, we use gross ultimate bearing capacity. Why is that? Because let's say here is a piece of land and this is your ground level, and I want to construct a spread footing here. So what we do, we usually cut the soil down there and then construct the footing here, and usually fill that part of that with like soil, usually granular soil. Okay, now if you think like there is no difference between the unit weight of soil and the concrete, which is kind of a like rough assumption, but you can see I cut the soil, I put this footing there, and then filled the whole thing with soil again. Okay, so that's actually the bearing capacity, gross bearing capacity. That's what we use here. Now, for Raptor mat foundation, most of the time we use net ultimate bearing capacity, which is actually your ultimate bearing capacity minus the surcharge, means like the pressure that's coming from the soil above it. Okay, so because you can see here that the construction of mat is a little bit different. So this is like a piece of land, and here is your ground level. To construct the mat, usually we cut a little bit deeper section, and then we put the construction here, but we never fill that one with soil because we make that one as a parking lot or basement. Okay, so you can see that we usually try to find out like how much net like load that it can take. Okay, so what is the net ultimate bearing capacity you can do here? So you are taking the weight of the soil there. Okay, so this is the bearing capacity of mat foundation in clay soil. Okay, for saturated clay, usually your phi equal to 0. We already know that for sand your cohesion is 0, and for clay your phi equal to 0. But you have to make sure that your soil is fully saturated to assume that your phi equal to 0. Because many cases you will see that if the clay is not completely saturated, then basically you cannot assume phi equal to 0 because this is not the undrained situation. Okay, the phi equal to 0 only for undrained situation when the clay takes much longer time to escape the water out from the soil. Okay, so here you can see when phi equal to 0, then basically your NC is equal to 5.11. We don't have any inclination assuming that one, so you can see like mat doesn't have any inclination force, so you can see this one is 1, this one is 1, and this one is also 1. but I didn't put that one here because when phi equal to 0, then NCC is 5.14, your NQ is 1 and N gamma equal to 0. Since N gamma equal to 0, this whole thing would be 0, okay? And you can see all other three factors here are 1 when phi equal to 0, okay? You can just set that one in the equation for QS and QD, and you will get that one actually 1, okay? So if you simplify that one, then basically you get QU equal to CU NC FCS FCD plus Q here, okay? Because all other factors are 1, and this one is 0. So Q is nothing but the effective stress at the bottom of the foundation, which is actually gamma DF, right? So if you find out the value of FCS and FCD and plug the value of NC as 5.14, then basically using this one, you get your gross ultimate bearing capacity of saturated clay, which is 5.14 CU. This is your CS shape factor, and this is your depth factor. And you can see this one is your Q here, okay? So the net ultimate bearing capacity in that situation would be QU minus Q. QU is the gross ultimate bearing capacity minus Q. But we already find that out, like QU is basically this one here. So if you subtract Q from there, then this Q and the other Q will cancels out, and basically you will get this part here, okay? And if you use a factor of safety of 3, then basically you can find out the net allowable bearing capacity. So this is nothing but net allowable is nothing but net ultimate divided by factor of safety. So if you use a factor of safety of 3, then basically you divide that 5.14 by 3, that's actually 1.71. So you can use this equation, or you can use the general bearing capacity equation. But this one would be much easier because this one has already been simplified, okay? So let's see one of the example of that one in the next page, okay? Now there is an example here that's 10.4 in your book, I guess. So determine the net ultimate bearing capacity of a mat foundation measuring 15 meter into 10 meter on a saturated clay, where CU equal to 95 kilonewton per meter square, phi prime is 0, and DF equal to 2 meter. Now, as I said earlier, you can use the general bearing capacity equation with phi equal to 0. If you don't want to use that one, then you can also use this one, because this is a simplification of the general bearing capacity equation for clay soil, saturated clay soil. So you can use this one, and then you can just plug all those values here. This is your B, which is 10, your L equal to 15, and your DF is equal to 2 meter. So everything is given here. So you just plug that one in that equation, and you get 595.9 kilonewton per meter square, okay? Compensated foundation. So you can understand that that for mat foundation, we cut a lot of soil, okay? Take that soil out from there, and we don't put that soil back. Now, let's try to understand that one, that you are taking that soil out, and if you put a building with the same weight like the soil you dig out, then basically the bottom of the foundation will not experience any additional or increased pressure. Okay, as you are taking, let's say at a depth of 10 feet, and the soil has, let's say, 100 pound per feet cube, like unit weight. So if you go like 10 feet, that like actually like 1000 psf, like, or 1 ksf uh, pressure that you are taking off from the soil. Now, if you put a building which will put like 1 ksf pressure there, then basically the soil at this foundation level will not feel anything increased pressure, because this soil was also having, like 1 ksf pressure by the soil above it. So if you make your depth in such a way that the soil doesn't take any increased vertical load, then basically we call that one uh, the fully compensated uh, foundation. Means like uh, the weight of the building has been compensated by digging out the soil from there. Okay. Using this design, a deeper basement is made below the higher portion of the superstructure, so that the net pressure increase in the soil at any depth is relatively uniform. It doesn't change, remains same. Because let's say for me, if I take my head off and put a rock here which has the same weight of my head, then basically my leg will not feel any difference. Okay, I'm just like trying to give an example. Uh, so if I put something like much, like less weight, then my leg will feel relaxed. Okay, if I put something higher than the weight of my head, then basically my leg will be a little bit stressed, because now they are having more uh, stress than what it has been experiencing before the change. Okay, so that's basically the same analogy you can use for the mat foundation. So you can see here that here actually the load is a little less, so you cut it less. If you have like more load here, you cut it more to make that one completely compensated foundation. So basically we are going to show you an example for that. So the net average, we are talking about the factor of safety of compensated foundation. Okay, so net average applied pressure on soil is Q equal to Q by A minus gamma dF. That's the pressure you are taking off by cutting your soil. And this is the pressure that's coming from the structure. Okay, now if it is fully compensated, like case, then basically this one has to be 0 here. Okay, so fully compensated case, your Q should be 0. Net change in stress has to be 0. So in that situation, your dF has to be Q divided by A. Just rearranging this equation, if this is 0, then Q by A is equal to gamma dF, and dF equal to Q by A multiplied by gamma. Okay. Now, factor of safety against bearing capacity failure for partial compensated foundation is given as factor of safety is Q ultimate divided by your Q. Okay, there's the change in your thing. So you can see this is your net ultimate divided by how much is coming. That's basically, you can change that one with this. Okay, so you can find out what would be the factor of safety against, like of your construction. Okay. So this is the factor of safety for construction in saturated clay soil, because you already know this is your, if you go back here, then this is Q net ultimate. So here, actually for clay soil, this is your Q net ultimate. So basically you don't have to use the big equation over there for general bearing capacity equation. You can just use this equation, which is kind of simplified for saturated clay when phi equal to 0. Okay. Now this one is a problem from your book. You can see the mat shown in following figures. This is the following figure here, which has a DF, depth of foundation, and the load coming here is Q. So the dimensions of 18.3 meter into 30.5 meter. The total dead and live load on the mat foundation is 111 into 10 to the power 3 kilonewton. Okay, the mat is placed over a saturated clay having a unit weight of 18.87 kilonewton per meter cube, and C undrained is 134 kilonewton per meter square. So given that DF equal to 1.52 meter, determine the factor of safety against bearing capacity failure. You can just use that formula and just plug all those values here. So what are those values here? You can see this is your B, this is your L. Okay, L is always bigger than B, right? So this is L and this is B. This is your total load, okay? Q, that Q here. What is A? That's this multiplied by this. That's the area of the mat. Your DF is given 1.52. Your unit weight is 18.87. This is 18.87. And your CU is given 134 kilonewton per meter square. So you just plug all those values here and you can find out your factor of safety is 4.66. Okay. Now let's move forward. The two methods that exist to design structural design. Okay. So we have conventional rigid method and we have approximate flexible method. Actually, conventional rigid method is much easier to do when you do like smaller building, and you can smaller and kind of simple, you know, like rectangle size building. If it is a L shape or like different shape, this and that, in that situation, it might be a little bit difficult to follow the conventional method. These days, actually, we use a lot of softwares to design that kind of, you know, structure. But you can do that one by, you know, like hand method. So we are gonna discuss the conventional rigid method today. We are not gonna discuss the flexible method because that would be too difficult to do that one on hand. Okay, so let's say for this, we are just gonna talk about the step-by-step procedure, and then I'm gonna show you one problem in the board, and it would be much easier for you to understand that what I'm doing over there. Okay, so let's say this is a rectangle area and I have like 4 columns in that direction and 3 columns, total 12 columns here. Okay, now what we first do, we try to find out the total column load. Okay, and then once we get the column load, and if the column load is the resultant column load is working at the center of the rectangle, then basically there is no eccentricity, right? But most of the cases, this is not the case. You will see, since the column load varies from column to column, and if you try to find out the resultant force and the location of the resultant force, most of the time you will see this one is not aligned with the center of the foundation. So that creates some eccentricity. Okay, so you have eccentricity in the x direction. If you have, you can have eccentricity in the y direction. So this is actually the soil pressure, like pressure or soil reaction or pressure from the foundation to any location is basically Q by A. That's actually the average pressure. And you already know this is actually the flexural formula, right? Your stress, normal stress is basically Q by A and MC over I. Now we have like moment in two different directions. So I'm just using two different, this is like MY means like the moment along the y-axis, and this is your moment along the x-axis, okay? X is the distance from the center to that point, y is the distance from center to that point, Q is the total load, and A is the area of the mat. So they are putting all those things here, that what is that I already told that one to you. Now we try to find out by taking the moment. We try to find out X bar and Y bar. And once you get X bar and Y bar, then subtract B by 2 from there and find out your EX because you took that moment. Let's see here. You see that took the X-axis here and Y-axis here, okay? But I would prefer, rather using the X-axis and Y-axis there, I would prefer to put your X-axis and Y-axis such a way that the origin would be actually at the center of the foundation, okay? So I did that kind, like situation in our, I'll just do that one in the board. You can just take a look, that would be much easier to solve, okay? I don't see any reason why my X and Y bar has to be here. I can just put like X and Y here and take the moment and find out EX and EY directly, okay? So there is no need like to have that X prime and Y prime because I already know this is the center of the slab here, okay? So once you get like this EX and UI, then you just plug all those values in your equation here and find out the pressure on soil at all corners, okay? And if you see that the pressure is, the highest pressure, maximum pressure is less than Q allowable net, then basically you are fine, okay? So your design is fine, okay? Now what happens, like if any corners has a little bit higher pressure than the allowable, capacity, net allowable capacity, then what do you do? What we can do is like, you can remember like in chapter 6, like when we had the simple, approach to eliminate the eccentricity. What we do usually, we try to add a little bit more, like not a little bit more, I'll just say like, let's say 2E in each side. So we'll try to make our foundation footprint a little bit bigger, okay? So what will happen if you see that one here, if you see here that if you increase your A, then basically your Q will decrease, okay? So if you increase your footprint of the mat, then basically you can reduce your Q, okay? But you cannot, extend that much there because you cannot go beyond the property line. But most of the cases you will see there is at least 5 feet in each of the sides. So if you just make your slab size a little bit bigger, then basically you will be fine because your pressure will reduce, okay? Now what we do, we just try to find out the average pressure, okay? like the average pressure, let's say for here, for IHGF, that's actually here, IHGF, just trying to take like a small strip here, okay? So what they are trying to do, you see, you can find out, you already know that Q1, Q2, Q3, Q4, that's working at I, H, G, and F. And then you try to find out the average, you know, like average soil pressure here, which is actually nothing but the pressure here and pressure here. You just add that two and get the average of that, okay? The total soil reaction, that would be equal to QAV into B1 into B. Okay, this is B, and in the other direction, the width of the strip is actually B. So you try to find out the total soil reaction under that strip. Okay. Now you just try to get the column load on that particular strip, like Q1, Q2, Q3, and Q4. But what you will see, the pressure coming from the top is not equal to the reaction. Why? Because when you cut a rigid member, actually, if you cut a rigid member here, then what are the component of reaction you will see there? So you will see normal stress or normal force, shear force, and bending moment, right? But for mat foundation design, we usually assume that there is no force working in that cutting section here. So that's why you will see, since we are ignoring the reaction here, so basically you will see there is some discrepancy in the pressure that's coming from the top and the reaction coming from the bottom. So we have to adjust that, okay? So how we adjust that? So as I said here, some of the column loads on the strip will not equal to Q average B1B because the shear between the adjacent strips has not been taken into consideration. So average load, that's coming from top, that's coming from bottom. So add them and get the average. Now, once you get the average, then basically you have to, like use a factor to multiply with this one so that you go to the average. You decrease that one to that average value. And here you have to multiply that one with a factor so that you increase your value to average value so that your force from top and bottom will match. Okay, so I'll show that one in the example here. So that's basically the example. I'm going to do that one in the board, which is showing that there are 9 columns here and there is a strip here, okay, A, B, C, D. So this one is saying calculate the depth of embedment for the fully compensated foundation, okay. The first find out the depth of foundation for fully compensated foundation. Then find out the pressure at A, B, C, and D. So A, B, C, and D, and then draw the shear force and bending moment diagram for that strip here. So I'll do that one and show that one in the board. But before I go there, yeah, I also posted another example problem here. Okay, I'll request you to take a look here because in that particular problem, they also talk about how to design that one like your reinforcement design and what would be the thickness, everything here, okay? This is kind of important because I'm not gonna ask that question for your exam, but definitely I'm gonna assign you your project, which might require that information, okay? So please take a look there. If you have any question, you can just ask me now, or you are also allowed to ask questions when you do your project. Okay, so let me go to the board and uh, try to do that example over there. Okay, so we are going to solve that one here. I already drew the figure for this problem. Uh, you can see here that 1,000, 1,300, 1,200, 1,000, 1,400, 1,300, 900, 1,100, and 1,200 kilonewton load is working down there. Okay. So first of all, I'll try to find out the B and L here. So you can see this is the longest distance. So that would be your L. So your L would be 6 plus 6, 12, 13, 14.4. Let me write it down. 6 plus 6 plus 1.2 plus 1.2. So total is 14.4 meter. So this one is 1.2. If you see here, then basically the size of the column is 80 centimeter, means like 0.8 meter. So half of that is 0.4. Okay, so from here, it's actually 0.4, and then from here to here, that's actually 0.8. And here to here, that's actually 0.4. So total is 1.2. So same way you can find out your B, which is basically 5 plus 5 and 1.2 and 1.2. That's actually 5 plus 5 plus 1.2 plus 1.2. That's 12.4 meter. Okay. So now we can find out the total weight that's coming down there. So total weight is 1,000 plus 1,300 plus 1,200 plus 1,000 plus 1,400 plus 1,300 plus 900 plus 1,100 plus 1,200. That's basically 10,400 kilonewton. Okay, so the pressure of soil, like below the foundation, you can just find that out, right? The sigma pressure is equal to P by A. So that's basically 10,400 divided by your area, which is 14.4 into that's actually 58.24 that many kilonewton per meter square. Let's say average. Because I'm saying that one average because if there is any eccentricity, which we'll check in the second part of the problem, then basically you will see some part has a little higher pressure than the other part. So we are just assuming that this is the average pressure. Okay. Now I have to, for 100% compensation foundation, this means like the pressure that's coming from the new structure should be equal to the pressure of the soil that you will cut out from there. Okay, so you are taking some weight off from there and then you're putting the building, same pressure building on top of that. So the soil is not going to have any additional load. That's actually 100% compensated foundation. So what is the advantage of that? If the soil doesn't have any additional load, then basically your settlement would be very, very negligible, close to zero, right? That's basically, like the understanding. Now, let's see that at what depth the pressure would be 58.24 kilonewton per meter square. We know that gamma of the soil 17 kilonewton per meter cube. So weight of soil or pressure at a depth of, if the pressure at a depth of, that's actually gamma. So pressure is basically gamma dF. Okay, this one has to be for 100% compensated foundation. This pressure has to be equal to the pressure that's coming from here. So I can just say 58.24. So my dF would be equal to 58.24 divided by the 17, which is the unit weight of soil. So we get 3.42. Okay, so basically if I cut 3.42 and take all the weight of the soil, the weight of the soil there has to be the same weight of this much. Okay, now we can just check that one. Let's check it here. So what is the total volume of soil? That's basically 14.2 into 12 or 14.4, sorry, into 12.4 into 3.42. And then the weight of soil that has to be this volume 14.4 into 12.4 into 3.42 multiplied by your gamma, which is 17. So that's basically 10,400 kilonewton. So this means like the total, like weight of the soil that you are taking out from there, actually you putting the structure with the same weight. So basically the soil is not, getting any, increased pressure from the structure. And you can remember, like for mat foundation, this is important because most of the cases we usually make our garage or like underground parking or basement. So basically we are not gonna put the soil back there, okay? So we are taking that soil out, we are making the structure there, and then basically the weight of the structure is same as the weight of the soil we took out, so no additional settlement or no additional effective stress on top of the soil, okay? Now, if I want to do like 50% compensated, so what would be my depth of, like foundation? That would be just half of that, sorry, the half of that, okay? If I want to say like 75% compensated, then 75% of this one. Make sense? Okay, now let's move forward. The second part of the problem is asking to find out the soil pressure at A, B, C, D here, okay? To find out the soil pressure, actually, we have to find out the eccentricity first, okay? So if I want to find out my eccentricity, let's say this is my x-axis and this is my y-axis. I just took the axis, which is the 0, 0 for the centroid of this mat foundation, okay, just at the middle here, okay? So you can see if I take the summation of forces in x direction, so you can see for this one, actually your is equal to 1200 plus 1300 plus 1200 multiplied by 6 minus this side here, 1000 plus 1000 plus 900 multiplied by 6. Okay, so this one is 6 this way, this one is 6 this way. So that's basically this moment is equal to your total force multiplied by Px. So we already know this one is 10,400. So you can find out your Ex from here, which is basically 0.46 meter. Similarly, I take the moment in the y direction, right? So you can see that if actually this one is total. Let me take that one total. Multiplied by EY. That has to be this force multiplied by 5 because this is the positive side. So you can see 1000 plus 1300 plus 1200 multiplied by positive 5 minus these forces 900 plus 1100 plus 1200 multiplied by 5. Okay, so you can see your EY is basically 0.14 meter. Actually 144 meter. Okay, so if I show that one here, so this one would be somewhere here. So this is your EX, and this is your EY. Okay, now let's move forward. Now I need to find out the moment of inertia in the X direction and Y direction. So your Ix would be BH cubed by 12, which is basically B is, this one is actually your B now. So 14.4 into 12.4 . Similarly, that's basically 2288 meter to the power 4. And your IY has to be, this side is B and this is H. So this one has to be 12.4 into 14.4 to the power 4 or to the power 3 divided by 12. That's basically 3086. Okay. Now we know our total force here, like total stress here. You can see the formula, like Q equal to P total divided by the A total plus minus MYX MXY divided by IX. Now you can see, since this is our origin, so everything this side is actually your X is negative, but your Y would be positive this way and Y would be negative this way. Okay, so so this one you can see your My and Mx, that's basically is equal to 10,400 multiplied by your Ex, right? So your moment, let's say moment here, we said moment is basically P total into Ex. So that's basically, that's actually moment along the y-axis. Okay, so that would be 10,400 multiplied by 0.46, which is basically 4794. that many kilonewton meter. And your M along the x-axis. This is your x-axis. So moment along this way, you know, that's actually P total into EY. That's actually 10,400 multiplied by 0.14. That's actually 1,498 kilonewton meter. Okay, so if I put this equation here, then finally we get that one is 58.24 MY. That's actually 4,791 divided by IY, so 3,086 X plus minus 1,498 divided by IX, which is 2288Y. So that's basically 58.24 plus minus 1.55x plus minus 0.65y. Okay. Once you get that equation, we can just plug the value of your x and y to find out the soil pressure at point A, B, C, D. Okay. So I'm keeping that one there. So pressure Q at A, that would be 58.24. So X is negative. So basically that would be negative 1.55 into negative, or let's say for A, negative is 6 plus 1.2, that's 7.2. Right? So this is the, you are measuring the distance from here to here. So 6 plus 1.2, that's 7.2. And then actually this one is also minus for y. So 0.65. And what is your y here from here to here? That's actually 5 plus 1 plus 1.2, that's 6.2. So if you do that one here, for point A, you get 43.02. Okay. Then for QB, you can see this is 58.24 minus 1.55. Now X is, the total is, this strip is 3 meter. So you have to say 7.2 minus 3, that's actually 4.2. Minus, for Y, that will remain same, So that's basically 47.67. Similarly, you can find out your QC, which is 58.24 minus 1.55 into 7.2 plus, okay, my Y is now plus. So that's actually 0.6565 multiplied by 6.2. So that's actually 55.78. And your QD that's basically 1.55 multiplied by 4.2 because point C here, so distance from here to here is 0.44.2 plus 0.65 Y is actually same, 6.2. So this one is 51.14. Okay. Once we get the soil reaction at point A, B, C, and D, then basically you can, what you have to do, you have to make a cut here, okay? A line cut along C and B to draw your shear force and bending moment diagram. That's actually the third part of the problem, okay? The biggest problem here, like when you make a cut here, you know, like for a rigid body, when we cut any section, there is like three components of reaction, right? One is the longitudinal stress or normal stress, shear stress, and bending moment, okay? But for simplicity, most of the cases, we usually assume that there is nothing working along the edge here. And because of that assumption, we have to do some, like measure so that your summation of forces in the y direction remain, like zero, because this is like kind of equilibrium situation, right? So what we do here, let's do that part. So you can see the average here. We know that we have like the stress here, 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 and here. So the average stress, the average pressure, that's the average pressure, that would be 43.02 plus 47.67 plus 55.78 plus 58.14 divided by 4. That's basically 49.4 kilonewton per meter square. So if I multiply the area of that one, then basically I will find out the total reaction, okay? So reaction force, which is actually 47.4 multiplied by this distance, 12.4 and 3. 12.4, and that's basically 1837.68 kilonewton. Now you can see the force coming from the top is like this one plus this one plus this one. So total force P is basically 1000 plus 1000 plus 900, 2900 kilonewton, right? So you can understand that basically the slab is not stable, right? There must be like some shear force working along that line. And how much is that? If you subtract that one from there, then basically you can get that force there, right? But we are trying to minimize that one. So what we are going to do, we are going to increase that reaction at a certain percentage and decrease that force at a certain percentage so that we are just at the middle of that, like compromise, okay? Just compromising so that this one has to be at the middle of these two forces. So you can see, so the difference here or the average here, average of this P and R, that's basically 1837.68 plus 2900 divided by 2. So that's basically 2368.8. So what I have to do, I have to multiply this force increase to here and this force decrease to here. Okay. So if you see the work factor to reduce my P, factor for reduction, that has to be 2368.8 divided by 29, actually 0.816. Okay, so what would be this load here? So the load 1000 will reduce to 1000 into 0.816, so 816 kilonewton. Similarly, this load here 900, that one is going to reduce to so this one has to reduce to actually 734. Okay, now I have to increase that one in such a way that this one, the total load here, this one has to be actually 2386.8 here. Okay, so how can I do that? So I'll just divide like the stress now, adjusted pressure. That would be 2368.6 divided by the area, 12.4 into 3, that's basically 63.67. So if the reaction is 63.67 and you multiply that one with that area, then basically your total load would be 2368. And if you add the 3 load after adjustment, that would be also, that would be also 2368.8. So now this one is in equilibrium. Okay, now you can draw your shear force and bending moment diagram easily. Okay. Once you adjust your stress, then basically you have to start drawing your shear force and bending moment diagram. I know you already learned how to draw the shear force and bending moment diagram, but in foundation engineering, like how we adjust that soil reaction as well as the load coming from the top, that's basically what I wanted to show you. But now you see that after adjustment, actually the summation of forces in the y direction is 0. So basically, if you draw the shear force and bending moment diagram, they are going to close at the end. Okay, this is the most important thing here. Okay, so now you can see here that this is like your CD, this side here. I'm just trying to rotate that one like this, just taking that one and putting like this. So this is your CD and this is your BA. So this one, we adjusted that one from 1000 to 816, 816, and 734. Similarly, you can see here is your, this one is 3 feet wider. So I multiplied with that stress with 3, and then become 191 kilonewton per meter length of the strip. Okay, that's the adjustment I did here. So now you can just start drawing your shear force diagram. This one looks like this. And then this one is actually, you can see this one would be 191 multiplied by 1.2. So that's actually 290, 229. Then this one, there is a big jump here, comes here. That's actually 727, 734 jump going down. So this one is 505. Then this one is going to go like this. And this one is actually 450. Then you have one more jump here. So this one is going to go here, which is 366. And then this one is going to go all the way up here, which is basically 589. And then there is a big jump here. And this one goes back to here. So this one is basically 226. Okay. So that's the way your shear force diagram works. Now, for bending moment, let's say this is shear force diagram. So this one looks like that. So this one is 137.5, 529. This one is very small actually. 346, 567. And there is a value because of that adjustment. You will see that there it may not go directly to 0. Okay. But the most important thing here from that area that you can see that the maximum positive moment is 529 and your maximum negative moment is 567. That's the thing you have to consider when you try to design your um, reinforcement and slab thickness and all other things. Okay. Um, but that's a completely different story because we are not going to talk about like ACI requirement and everything. Sometimes you might have to use the factor load if you follow that method, or you can use a factor of safety. That's up to you. But that's basically what we do, right? Then we can take another slice in vertical direction. We take slices in the horizontal direction. Then we try to find out, hey, how much reinforcement I need in the horizontal direction. Okay, that's the way we move forward. I just posted another homework, another example in your, like handout, and you can see that how they use that design, like for reinforcement and other things. So most important thing, like for mat foundation is actually the punching shear. So that's always governed to find out the thickness of the slab. So you can just take a look with the other example. If you have any questions, like please contact me as soon as possible. Okay. Thank you so much.